Hi, everyone. Our last lecture ended with a bit of a cliffhanger. We were in the middle of proving some basic properties of Galton-Watson processes, a type of branching process. And today we're going to finish that proof, and then we're going to use those properties to explore some new concepts. We're going to look at the long-term behavior of the populations that Galton-Watson processes model, and we're going to talk about extinction, the dying out of those populations, or the chance that those populations could go to zero. We're going to introduce new terminology and new tools for describing extinction, and then we'll make a couple of proofs about basic aspects of extinction. Let's get started. Today we're going to pick up where we left off in the last lecture, and we were in the middle of a proof. Normally I like to write things down at the same pace as I would on a blackboard because I think that's a good natural speed limit for how fast people can think and process information on their own. However, in this case, we're starting off in the middle of an argument, and you probably have already thought through and written down the information I wanted to start off with, just to kind of remind you where we were. So we're continuing a proof that we were partway through in the last lecture. The notation for the things that we had so far was we've got a Galton-Watson process that's written as xn, x sub n. It starts off with an initial population of 1. The expected size of the first generation after that is mu. That's just the definition of mu. The variance for that is sigma squared. Again, that's just the definition for that symbol. And we had already proved that the expected value for the population at time n was mu to the n. That was the first part of the proof that we were working on. And the second part was to try to show the following formula for the variance of the size of the population at time n. And it's expected to have this, so this is what we were trying to show, is that it has this piecewise defined result. So if mu happens to have the peculiar value of 1, then it has this simple form. And if mu is anything else, it has this little more complicated form. And we were most of the way there. We had shown that the variance looked like this, and we were kind of working on this last term here, the second derivative of this probability generating function here. And we had gotten relatively far with that probability generating function. We had it like this. We had it written in terms of the PGF for the offspring distribution, or z, which was the same as x1, evaluated at 1, multiplying this mu to the n minus 1, and then multiplying this sort of piecewise thing. So if mu was 1, it's multiplying n, and if mu is not 1, it's multiplying this ratio here. So that's where we were last time, and I'm just going to pick up from there. So the very first thing I want to do is just to remind you, so the quantity g here, g of s, is the PGF, the probability generating function for the offspring, but it's also the probability generating function for x1. And that was just, we'd shown that, I think, in a previous proposition. That's just because x1 actually is equal to the offspring variable. And so as a result, we can go ahead and use, we'll start off by using a proposition from way back in chapter 1. So from chapter 1, or I don't know what it was, lecture 2 or 3. So from long ago, we had a relationship between the probability generating function and its variance, and the variance for the variable that was the PGF for. And so we have the following thing. We had shown that we'd used many times, I think, maybe in slightly different form, but we had the following relationship, that the second derivative of the PGF evaluated at 1, in this case for x1, or for z, it's the same, is given by the following. And here I'm putting in the symbols for the variance that we already have defined, and the expected values. So it's minus the expected value, and then plus the square of the expected value. And so that's a relationship that we had before. And so we're going to put this, we're going to use this here and put it in there and clean up our result. So we just have a little bit of algebra to do remaining, right? So we have the following. So we have f double prime evaluated at 1 is this quantity here times mu to the n minus 1 and I'll just put in parentheses here. I'll just put that to represent the carrying over of that kind of messy looking piecewise part, which we'll deal with in a second, right? Okay. And so if that's the case, if I want to go back to the variance formula, right? So here's the variance. I'm going to take this for f double prime n and put it in here. And what I get is the following. So I get that the variance of x1 is equal to, and I'll just add on the parts, the part that was up here, mu to the n minus mu to the 2n, and then add on to it this piece that I just wrote. So I'll just copy it like that. Okay, and now we're just going to do really just some simple algebraic tidying for the two different cases. For the mu equals 1 case, you can probably already see the result, but so let's just write it out. So mu equals 1 case. So for that case, the variance has the expected form. All right, so if this is 1, this is 1, so this quantity here is 0. This is 1, this is 1, so this quantity is 0, and then this is 1. So all this stuff here is just sigma squared. And if you look at the parentheses here, the piecewise bit, when mu is 1, that's n, right? And so this has the expected form here. This is sigma squared times n. Maybe you would written that as n times sigma squared. I don't know, but it's obviously the same. N times sigma squared. Let's just do it the same. Why not? Because I'm a little bit weird. So we'll put the n in front. Why not? Okay, so that's the mu equals 1 case finished. And now we'll work on the general case. So if mu is not 1, here the algebra is just a little bit more. Right, we just have to keep track of all that stuff. So I'm just going to rewrite it and put in, where is it? This quantity here. Right there. Right, so I'm going to steal this guy. Right, and this is the variance, of course. I should have just kept the whole thing. Why don't I just take it all? Right, so I've got this guy here. And then the quantity that I'm going to multiply by mu to the n minus 1 over mu minus 1. Okay, and let's see, so what do we want to do with this first? So I guess we'll distribute the mu to the n minus 1, and we'll just look at the various different, in the parentheses there, we'll just look at what we get. So we're going to get sigma squared multiplying some stuff. So what is sigma squared multiplying? Sigma squared is multiplying mu to the n minus 1 times the ratio mu to the n minus 1 over mu minus 1. And then the next term, I'm I'm just going to isolate, keep the mu to the n from the very beginning of this expression. So this guy here, and then this guy here. Right, and then I've got, what do I have here? I've got mu minus 1 times mu to the n. Right, so this is this quantity here factoring out one power of mu. So I've got mu minus 1, and I multiply that by this guy here, and I get mu to the n. Right, and then this ratio. Oops, the minus 1 is downstairs. Like that. Okay. So this term stays the same. And I've got mu to the n minus mu to the 2n times, now this guy cancels with this guy, and when I multiply this thing through, what I get is mu to the 2n minus mu. Sorry, this was meant to be a plus here. Like that. And so all these guys disappear. They balance, and we're just left with the answer. That we were going for. And that completes the proof that we started in the last lecture. So we now have general expressions for the expected value of the population size and its variance at an arbitrary time step n. Okay, so now let's take a look at what happens to these quantities over long periods of time. So the general idea here is you want to know, what happens to this population. And so it's interesting to have a look at these expected values in the long time limit, so n going to infinity behavior. And of course we could have done this right before we did the proof, but I feel like you're not really allowed yet until you've done the proof. Okay, so let's think about first the case where mu is smaller than 1. Right, so this is where the expected value of the offspring distribution is 1. Right, so is smaller than 1. So if that happens, if we go back up to our formula, let's steal the results somewhere. Let's grab them just here. Bring them down here and put them off to the side so we can kind of discuss them. So over long periods of time, when mu is less than 1, so if n goes to infinity, so this is this is what you should have in your mind over here. Then the expected size of the population at time step n is 0. Right, so for this case, the expected value of xn is 0 at long time. So maybe you shouldn't put equal, just put an arrow. It goes to 0 as n goes to infinity. And the variance, which is harder to see, but let's go look over here. So when you take the n goes to infinity limit here, and mu is smaller than 1, so this thing goes to 0. So this term goes to 0 and will kind of annihilate everything. And so the variance also goes to 0. So the population is going to go away, and this is called subcritical. Right, this is this case of mu less than 1. So let's move this guy down. We'll leave this label up there. All right, and the next case I want to look at is mu is equal to 1. And that's a little bit of a curious, I mean, of course, it's a very peculiar setup. It means that you expect every member of the population to reproduce itself exactly, well, the expected value is 1. And this is called critical. And so if mu is 1 here, then the expected value is 1. So the expected size of the population at late times is 1, which is sort of interesting. It's always 1, the expected size. And the variance, so we just need this guy here, as n grows, is infinite. Right, so that's a little bit of a curious result. If you think of this as having some distribution, the expected value is 1, but the spread of the distribution is infinite, so it's a bit of a weird scenario. And then the third case we want to look at is the mu is just bigger than 1. And this guy, what is his name? I don't think we have a name for this guy. Critical and subcritical are all we're going to give names for. So for this guy, if you look at these quantities, so the expected value is going to blow up. Right, so this is infinite, and the variance is also infinite. Right, you just need to pay attention to this this one term here, and that will grow faster than all the others. Well, it's going to blow up. This guy here. So is this guy. Yeah. And so these are the kind of 3 typical behaviors for the population over long times for the different types of mu's. So it's super important. So this mu equals 1 value, which is sort of peculiar, is special. If you go just to a little bit smaller or a little bit bigger, then over long times you get very, very different behavior. All right. The people who worked on this initially were primarily interested in whether or not the population would just die out. And so we're going to do a little bit of work on that. And so we're going to introduce some terminology and some symbols to help describe that. And so the topic we're interested in here now is extinction. All right, so what are the conditions under which the population just disappears over time? And so, or maybe not at necessarily super late times, but ever, or at some specific time, say. And so to describe this, we're going to introduce some new symbols, some new terminology. So we're going to name A sub n. That's going to be the event. So this is the event that... so I guess it's a set that x sub n is equal to 0, right? So some specific, so it means that you're extinct at time n. That the population is extinct at time n, right? So that's the event. And we'll say E sub n. All right, that's the definition. So this is the probability of that event. Right, so it's the probability, in other words, so it's the probability that x sub n is equal to 0. All right, so that's the probability that you're extinct, or that the population is extinct at time n. And then we're going to say we're going to define A and E with no indices underneath them, no subscripts. So A with no subscript is going to be defined as the limit as n goes to infinity of A sub n. Right, so this is the event extinct eventually. Right, and lowercase e, this is going to be the probability of that with no index underneath it, lowercase e. Right, so this is the probability of eventual extinction. All right, so for the remainder of this lecture, we're going to work on a couple of propositions associated with extinction. But before we go with that, before we do that, we're going to have to make a funny sort of an assumption. So this is an assumption that we're going to require for these, for the little propositions that we're going to prove. We're just going to suppose that branching is possible. That is to say, so we're going to require that the probability mass function for the offspring is not always zero. It's non-zero for some non-zero values. So in other words, we require that p sub k, which we'll use to represent the probability that z is equal to k, is positive for at least for some k. Greater than or equal to 2, right? So it can't be the case that net branching never occurs, right? So we're not going to allow that kind of odd scenario. So we're going to make this requirement going forward. And yeah, so I just wanted to say that. And now let's work on our little propositions. I'm going to give these ones names, or not names, but numbers. So proposition. So this one I'm going to call, I think this is the same number that you'll see in your notes. This is proposition 4.3, but you could call it whatever you want. You could call it Fred. That doesn't matter. Just want to give it a name. So this is going to have two parts. And the first part says that the extinction probabilities get increase as the time goes forward. So in other words, 0 is less than or equal to the probability of extinction at time 0, which is less than or equal to the probability of extinction at time 1. Let me start this over. 0 is the probability of having extinction at time 0, right? Because at time 0, we have a population of 1, so that's not possible. But going forward, the probability of extinction at time 1 is bigger than the probability of extinction at time 0. That sort of seems reasonable. But this pattern continues. So this is E2 is bigger than E1, E3 is bigger than E2, or at least as big as, and so on, up until En and En plus 1 for all n values. All right, so that's the first part of the proposition. And the second part says that the probability of ever having extinction, of eventual extinction, is just the limit as n goes to infinity of E sub n. It might seem super obvious somehow if you think about the definition of A is the limit that n goes to infinity for A sub n, but those are the events and these are the probabilities. So I don't know, maybe it's a little bit subtle. All right, and so the next proposition, I don't know why we don't just make this one proposition. Probably should have done that. All right, and so we'll call this one 4.4. Right, so this one also has two parts, and the first part says that En, so this is using the probability generating functions, says that En is equal to the probability generating function for the offspring evaluated at En minus 1. Right, so En minus 1 is the probability of extinction at time n minus 1. So this is for n greater than or equal to 1. So that's the first claim. And the second claim is that the probability of being extinct ever is the probability generating function evaluated at that probability. But so what's funny here is we're going to say S equals E. In other words, E is the smallest root or smallest solution of the following. Okay, in the range 0 to 1, in the interval 0 to 1. There can be multiple solutions there, and so E will be the smallest one. All right, now we're going to work on the proof of the first proposition. So we'll say proof of 4.3, proposition 4.3, right? And so we'll do this in two parts, and we're going to just break things down in terms of events and outcomes and so on, and work with the basic principles of probabilities. So the first part that we're trying to prove, so let's go back and remind ourselves what this is. This is talking about the relative sizes of these probabilities, the probability of extinction at size, or at time n, and how it always grows. Right, so for this, we're going to say, suppose, okay, since you have the following, the event xn equals 0, this event implies that xn plus 1 is equal to 0, right? So if you're extinct at time n, then you will be extinct at time n plus 1, right? That makes sense. Then, therefore, what you have is that a sub n, so that's that event, the event xn equals 0, is a subset of a n plus 1, right? So all the outcomes that cause extinction at time n are a subset of all the outcomes that cause extinction at time n plus 1, right? Therefore, if you use the following, so then if we say that the probability of some event is given by the number of elements in B divided by the number of elements in the sample space. There's shorter ways to write this, of course, in the sample space. So what I'm saying, of course, is this. Right? If we take this to be the probability of B, then it follows that the probability of A sub n is less than or equal to the probability of A sub n plus 1. Right? And then that means, of course, those are E sub n and E sub n plus 1. All right. Okay, so that's the first part. Now we'll work on the second part. And just remind you what that is. The second part is saying that E is the limit as n goes to infinity of E sub n. Okay. So for this, let's define the following. So we're going to define some disjoint sets. Right, so I'm going to define D sub n to be the set of all x's that are in A sub n, but that are not in A sub n minus 1. So such that x is not in A sub n minus 1. Right, so these are all the outcomes that cause extinction at time n, but that don't cause extinction at time n minus 1. Right, so in other words, this is A sub n, depending on how you want to, whatever your favorite notation is, you might write it like this: take A sub n minus 1, or some people write it like this. That's fine, whatever. This is set subtraction. Right, so remove the parts that are in A sub n minus 1 from A sub n, and that tells you, that's the definition of D, right? So then these guys are disjoint or independent, right? So that is to say di intersection dj is the empty set if I is not equal to j. And it follows that A sub n is the union of all of the d's. Oops, I always make that mistake. A sub n is the union of all the d's for the earlier n's. So right, so that's how you build up the event A, or A sub n. And therefore, the probability, since those are disjoint, the probability of A sub n is the sum over, oh, how do I want to write this? I guess I'll use I, 1 to n, of the probabilities of the d's. Right? Okay. So, and what can we going to say here? So E is the probability of the event A, right? So it's just the definition. So the probability of eventual extinction, that's E, where A is the eventual extinction. And so that's equal to, by the probability axiom, I think the third axiom, I think, you have to look back at chapter 1, I think. So this is now the sum of I equals 1 to infinity, right? Because A sub n, right? So A sub n is this guy. Sorry. A, oh, erase, come on. So A is this limit here. Right, so that means this thing is true. And so this is the limit. Just rewriting that line as a limit. Oops, so that should be an n. Right? And so this is the limit n going to infinity of these sums, I equaling 1 to n of the probability. Or sorry. Boy, I'm rushing a bit. Let's take this out. Right, so this quantity here, the sum of all these probabilities, if we go back up here, Where did I write it? Somewhere? Where are you? Here. Boy, I must be getting tired or something. Okay, so that's the probability of a sub n. And so this is the limit as n goes to infinity of e sub n, because that's the definition of e sub n. All right, now we're going to finish off by proving the second proposition, 4.4. So this is a proof of 4.4. And this one, so we're first going to deal, again, it has two parts. And so if you remember right, let's look back here. What does it say for the first part? The first part says that e sub n is equal to the PGF G evaluated at e sub n minus 1. And that's supposed to be true for n greater than or equal to 1. So let's see how we do that. So we're going to use a kind of clever trick for this. So notice the following. So notice that you can write this probability generating function f sub n evaluated at 0. What does that give you, right? So let's put in the definition. So this is the sum as k equals 0 up to infinity. And so this argument was normally s, and so we'd have s to the k. And so I've got 0 to the k times the probability that x sub n, x at time n is equal to k. Right, so that's just the definition of the PGF here. And in this sum, all these terms get made 0 by 0 to the k, with the exception of k equals 0. And so this is actually just equal to the probability that x sub n is equal to 0, right? And that's the definition of e sub n, right? So we can write e sub n as the PGF f sub n evaluated at 0. Okay, so let's do that. So we'll say e sub n is equal to this guy. We just showed this, right? But then by the proposition, one of the propositions in one of the things we proved in the last lecture, f sub n is the probability generating function for the offspring evaluated at f sub n minus 1, which if further evaluated at 0, right? Just because there's a 0 here, and so it goes here. All right, but then by the same reasoning, you know, f sub n evaluated at 0 is e sub n. That's true for any possible n, and so this must be the PGF G evaluated at e sub n minus 1. Okay, so that's the proof for the first part. Oh, I should have labeled that. That's the first part of our proof. Okay, and so let's go back and look at the proposition and see what was the other half. Where are you? Here you are. Okay, so we've just shown this guy. And the last one we want to show is a little more tricky. We want to show that E is equal to the PGF for the offspring evaluated at E in such a way, so this is the sort of little bit delicate part, that E is the smallest root, the smallest solution to this thing in the interval 0 to 1. Now part of that is sort of trivial. E is a probability, so it's definitely in the interval 0 to 1, and so I won't really bother with that bit. That's guaranteed that it's in that interval. But let's see how we do this proof, right? So the first thing I'm going to say is that E is, we already showed this, it's the limit as n goes to infinity of E sub n, right? So that was in the previous proof, right? And so then I can write this as the limit. I can just take this previous result here, just right above, the limit as n goes to infinity of G evaluated at E sub n minus 1. right? And now, because g is a continuous function, this is the same thing as g evaluated at the limit n goes to infinity of e sub n minus 1. And that's the same thing as e. Right, so that part is straightforward. So e is equal to the PGF of e. Now the harder part of this proof is to show that it has to be the smallest such solution, because there can be more than one solution. So we'll do this by induction. So show smallest root or solution, however you want to phrase this, by induction. Okay, so let's look at the n equals 0 case, the base case. So n equals 0. So for that, we have e sub 0 is actually equal to 0, right? That's the definition. The probability of being extinct when time is 0 because we have a population of 1 at that time. And that's less than or equal to any s in the interval 0 to 1. All right, so it's certainly less than or equal to any s that satisfies this root. Okay, so it's all right for the base case. And now what we want to show is that if it's true for n, it implies that it's true for n plus 1, right? So suppose that it's true for n. And how we're going to write that, we're going to say, suppose that e sub n is less than or equal to, I'm just going to take this. Less than or equal to s in this interval where s is equal to g sub s. So that's just supposing that it's true, that it's the smallest root. And then we're going to do this kind of funny trick. All right, so notice we can take the derivative of the PGF, and if you do that, if you look at the definition of the PGF, when you take the derivative with respect to s, normally we'd have a sum of k over k equals 0 to infinity of s to the k times p sub k, so I'll sort of partially write that. But if I take the derivative of this with respect to s, I get k minus 1 times k. All right. And if I look at this sum, so the first term is never going to contribute because k equals 0 will annihilate that term. Will annihilate, yeah, so this is actually the same thing as the sum of k equaling 1 to infinity of k times s to the k minus 1 p sub k. And that has to be positive, right? I think that's by our, by our condition that we assumed at the start that branching is possible. So one of those p sub k's has to be positive. All right, and so what this means, so if the derivative is positive, right, that means the slope is always positive. So this means, so therefore, or so, the slope is positive. It means that this guy is always an increasing function of s. All right. So then what we've got is we do the following. So we say, okay, so g evaluated at e sub n, right? That's less than or equal to g evaluated at s. This is the assumption, right, way back here, right? And this guy is equal to s on the right-hand side, right? And by the proposition, when you evaluate g at e sub n, you get back e sub n plus 1 by one of the things we proved previously. Okay, and that completes the proof. So there you have it. We've seen what extinction is for Galton-Watson processes, and we've seen how extinction probabilities relate to each other at different times, and we've seen how extinction probabilities relate to the generating function for the offspring distribution. And that's all for today.